Welcome to the television studio at Ladue Horton Watkins High School for today's HEC-TV Live program, The Science Behind Weather Forecasting. Hi everybody, I'm Tim Gore, your host for the program today, and I'm very happy to welcome you to this location where you're going to have the chance to understand what it's like to be a meteorologist. We're going to interact with Fox 2 Television's Chris Higgins. Come on in, Chris, who's going to give us an idea about what that's all about. Thanks very much for being with us today.
Thanks for having me in.
We're glad to have you. We're going to learn about what it's like to forecast on both a good weather day and a not so good weather day, and we're welcoming your questions throughout the program. As always, we've got interactive groups joining us via video conference, but don't forget, if you're watching us on television or the web, you can email your questions to us at live@hectv.org. That's live@hectv.org. They'll come straight to my phone, and I look forward to introducing them into the program. Students here at Ladue actually had the chance to meet you, Chris, earlier.
Very cool.
And create a tour of the weather station and the weather studio right there. And I want to invite Samantha in right now. Samantha Whale from Ladue Horton Watkins High School. Thanks for being with us.
Thanks for having me.
So you're part of the Ladue Horton Watkins TV program here. Samantha, how long have you been doing that?
For 3 years.
And what was it like to go and produce the segment that we're about to see?
It was really interesting to see a professional studio and look at all the tools that Chris is using behind the scenes to get that weather forecast ready for airing each night.
And you were joined by who from your school to do that?
Lillian Donahue.
And it's Lillian that you're going to see right now as we roll this tour.
Thanks, Tim. We're here at the Fox 2 Weather Center, and we're going to show you some of the tools of the trade on how to predict weather.
As we begin to look at this now, Chris, and we see you standing in front of what is your green screen there, what are we seeing here?
This is our weather forecast center. We kind of have it broken down into a couple areas. There's the actual area where we ingest and look at the raw data and use it for creating the forecast. That's the couple computers we just looked at. Then there's the display area where we pretty much get to what we call PowerPoint on steroids. It's how we actually get the weather forecast to the viewers at home. And then there's our warning desk, and that's where we sit down and where all the short fuse or immediate warning information comes in, stuff like the Doppler Radar, when there's immediate life-threatening information we need to get to the public.
Okay, so we're seeing all these computers here. They're giving you all sorts of different kinds of data then.
Yeah, exactly. We've got the one side, the forecast data. There are any number of different weather computer models or computer simulations that take the current state of the atmosphere, turn it into numbers, pump it into a bunch of computers that then create computer simulations. Then myself as the meteorologist interprets that information and kind of puts the pieces of the puzzle together to try and create the most accurate look at the future with the forecast.
And those graphics are what you're sending out to the world to make sure that they understand it all.
Exactly. You know, I can be the best forecaster in the world, have it exactly right, but if I'm not able to make that forecast and communicate it well to the audience, then it goes unnoticed.
Now, how did you go about becoming a meteorologist?
I was interested in meteorology as a kid and was able to feed off that going to college. It's a lifelong dream and a passion for me. Went to St. Louis University here in St. Louis. Have a Bachelor of Science in Earth and Atmospheric Sciences and Meteorology, and my emphasis is on severe local storms and thunderstorms.
Oh, very cool. Now, today we're going to look at two different days. One that's a very nice, low-impact day, as you all refer to it. An easy day. Yes. And another one that was, of course, a bit more exciting from a weather perspective, a very difficult day of St. Louis area weather. Talk just a little bit about the nature of putting a forecast together. You're getting information from the National Weather Service. Mm-hmm. Is there a time frame that you're always working with? Or?
You're always looking for, one thing about being a meteorologist, you're never really off duty. You're always looking at the state of the atmosphere right now and looking for clues that Mother Nature gives. And it's not just here in St. Louis. We're looking at weather data all around the country, really all around the globe, from St. Louis all the way up into Canada, west into the Pacific, all the way to Japan. That's where weather systems that affect us generally originate from. So we have to look way out into the Pacific and also out our back door, because there are small things that can develop out west that migrate into our area.
Okay, so then before we get to the place where we're going to see something like this, we'll bring up image 46, which is a weather map that we would see a lot of times on television. So there's a lot of work that goes into what you do before we see something like this then. Exactly.
The National Weather Service, in tandem with the Federal Aviation Administration, takes weather observations at airports all over the world at the top of every hour. And we take those observations, and we're going to see a map here in a little bit where we plot them on a map, the individual stations, and we identify weather features using that information. So like what you see there, you have warm fronts and cold fronts, low pressures, the red L's, or high pressure, the big blue H's, and precipitation areas. All of that is generally garnered from or taken from those weather observations. And that's the first step, is getting an idea of what's going on in the atmosphere right now and then we use the computer simulations to project into the future.
Now, I see those H's, I see those L's, but how do you know that's where they are? That's where this other map becomes important.
Exactly, and that, again, it's sort of a connect the dot exercise. So if you went to first grade and can connect dots, this is a good one for you.
Well, let's bring up image 40, which is an example of what's called a synoptic map.
Yes.
Which is that? Talk about this.
This is a synoptic map, which means big picture. Synoptic means big picture. And it's over the United States, and this is a surface level. We actually measure the atmosphere all the way up to 100,000 feet using weather balloons, which we'll talk about a little bit later. But this is from surface observations, and each one of those little dots with the little arrows on it, those are weather stations that are reporting weather information, and that all those different numbers mean something. You have the wind barbs that show the direction the wind is blowing from and how strong it is. And it also, in the upper right-hand corner of each one of those little station plots, is a 3-digit number that represents the surface air pressure, barometric pressure. By connecting dots of equal pressure on the map, we start identifying centers of high pressure and low pressure. In the end result, it ends up looking like a topographical map. High pressure is essentially a big mountain or mound of air. It'd be like looking at a hill on a topographical map, and then low pressure would be the valley.
Now, we've got a really lovely day here today, and we've got some video of the exterior of Ladue High School, so as we begin to talk about a good weather day, you can see it. Now, is it a generally true statement that high pressure means pretty weather and low pressure means potentially bad?
Yeah, I mean, there's always exceptions to every rule, but generally speaking, high pressure, you get high pressure sunny skies, partly sunny skies. Depending on the time of the year, it's either cold, warm, but generally it's a nice weather pattern with high pressure. Low pressure, if you see that coming in, then you start to look out for unsettled weather, whether it be thunderstorms, snow, depending on the time of year, or just rain.
Now, one of the important elements of your forecast, obviously, is the infamous temperature gauge. Will it be warm enough for me to actually go and play golf today? Will it be too cold for me to walk my dog? All that kind of stuff. And we want to look at a specific day, March 15th of 2013 this year, to talk a little bit about temperature. So we're going to bring up image 17 here, which gives you some temperature data from that day. At 12:51 a.m., it's 38 degrees, there's a 5-mile-per-hour wind, humidity is 73%, and we notice in the early morning hours it's pretty steady. It's like becomes 34 degrees by 7:51. But like as you think about predicting overnight temperatures, what are you looking at for that?
One thing we're looking at is the amount of moisture that's in the air, the relative humidity, and more specifically the dew point, which is the measure of how much moisture is actually in the air. Is very important. The temperature can never go below the dew point. So if we look at the dew point and we know, well, we know it's not going to get any colder than that. It's usually within 3 or 4 degrees of that temperature. So that's a good starting point. Then you decide, you have to look at the winds. How strong are the winds going to be? If the winds are stronger, that tends to keep the air mixed up a little bit and doesn't allow the cold air to settle as much. If the winds are lighter, those are typically nights where the atmosphere cools closer to the dew point and it gets colder.
Now, does the direction of the wind matter much, or is that mostly because of where the front is coming from?
It can at night, depending on where you are. Like if you're, say, in San Francisco and you have a wind blowing off of the California coast or from the coast on shore, that's cooler water along the Pacific coast. That can cool the temperature more. If you're in an area like Florida, for instance, as well. A nighttime breeze off the ocean typically can actually, because the water is warmer than the ground temperature, can actually force the temperature up near the coast at night.
I want to go back to that image we just saw again, back to image 17, just to remind folks of what it looked like in terms of temperature. It's 34 degrees at 7:51 a.m. And this, you all may not remember March 15th this year for any particular reason, but you're going to notice that it became a very lovely day. As we go to the next image, 18, slide 18, we're going to see that by 1:51 p.m. in the afternoon, it was 70 degrees. So we rose by nearly 40 degrees worth of temperature in a relatively short period of time.
Yes.
What causes that to happen?
Well, one year in March, and you're well past the winter solstice, which is the minimum of solar energy from the sun. So you're actually getting as much sunshine in the middle of March as you are late September, early October timeframe. So it's roughly the equivalent there. The other thing, besides a full day of sunshine, we also had southerly winds, and wind direction during the day has a big influence on temperatures because if the wind blows air from that region along with it. So if the wind's blowing from the south, it's going to blow warmer air in. If it's blowing from the north, it blows colder air in. There are a few exceptions to that, but in general, if a southerly wind, sunny skies, you can generally count on, at least in this part of the country, in the Midwest, warmer temperatures.
Okay. Now we want to go to a Doppler radar image of that that shows you very little, image 26 actually, which is going to designate for you what is a pretty day on the radar, and there's nothing here.
No, this is we look at the radar and turn it off for the day when something like this.
Now that blue stuff I often hear referred to as ground clutter?
That is correct. The fancy term is anomalous propagation, and it'll be on a spelling test near you someday soon. Don't ask me how to spell it though.
Oh, doggone it, I was about to do
I
that.
always had an extra N.
Instead, I'll ask some of these questions. I'll ask that some of the students from Ladue, and they can impress Mr. Vetter.
There you go.
Okay.
Basically, all it's showing us bugs, dust in the air, things that are close to the radar. We have the ability to turn up the volume, so to speak, on the radar, and if we want to look for very fine particulates, we can crank up the juice and make it more sensitive so that we can see more things. Or if we want to turn it down and get rid of some of that, we can do that also.
Is it a general statement of truth to say you're more likely to have a greater degree of accuracy on a day like this than on a day that's going to be like the bad weather day we talk about, or does that just not really matter at all?
I think it's more that people don't pay as much attention on a day like today. If it's 70, 75, who cares? It doesn't matter to anybody. The difference between 1 inch of snow and 3 inches of snow can mean the superintendent keeps school open or closes school depending on where you are. And so people, at least in this part of the country, in the Midwest, get much more wrapped up about snowfall amounts. You know, if it rains, you don't care how much it rains, quarter inch, an inch of rain, whatever. But that difference in rainfall amounts, if you converted it to snow, would be the difference between 2 inches and a foot of snow. So in winter, it tends to get amplified.
Wow. Well, there's some information just about the basics of weather forecasting in relationship to a good weather day. We're going to switch gears in just a moment and begin to talk about a day with a lot more activity. Carson Elementary School in New Jersey, a question from you guys?
Yes, we do have one question today. Makai?
How long does it take to get an accurate measure of the weather?
Oh, how long does it take to get an accurate measure of the weather?
It depends what you're measuring. There's different things that we measure in the atmosphere. We measure snowfall, and when we measure snow, there are a couple different ways to do it. The unscientific, kind of the home use method for you at home would be to go out to your backyard with a ruler, measure in 5 fairly wide open places, and then average those numbers together. That's a general rough estimate for snowfall. Rain, we use a rain gauge, and you just look at the rain gauge. Temperatures, it's the instantaneous temperature that we read, which it's not an average temperature that we give you for the high for the day. Probably the one that requires the most time to actually measure is the wind. What we give you is an average wind speed over a 1 minute time frame, and then also the peak gust in that time as well.
This comes from Elizabeth Ann Seton School. What piece of new equipment technology do you find most helpful?
Without any question, Doppler radar, and there was a new addition to the Doppler radar called dual polarization that gives us some incredible insights into not just the rain that's falling out of the storm and the motion that's in there, but whether it's rain, whether it's hail, and how large the hail may be, and whether or not it's snow, and if it's big snowflakes or little snowflakes, because little snowflakes tend not to accumulate as quickly, bigger ones tend to accumulate faster.
Well, let's talk a little bit about dual polarization video since we just had that question about it. We're seeing an example of a radar location here. And so what are we seeing? This is the radar dome. It's called the Ray Dome. It looks a lot like a satellite dish, and I believe we're going to have an explainer video coming up here in a bit, but it's a lot like shooting a flashlight out into a dark night. When the light reflects off of something that's out there, you see it. When the radar shoots out into the cloud and it sees something, it reflects energy back, and the computer generates that. Depending on how much it sees, it turns it into a color representation. Now, the dual polarization lets us see the raindrop from both a vertical and a horizontal perspective, right?
Yeah, the old type of radar we used to have just showed us that there was something there. It couldn't give us any indication of the size of what that particle was. Now, because basically dual pole shoots the beam through, and we get a horizontal and a vertical slice of the raindrop, or whatever it is that it's seeing, we can get an idea of the shape. And that is very useful in determining if it's hail, if it's debris from a tornado that's being sucked up off the ground, which will be very irregular shapes. So there's a lot of insight. And we're really just beginning to learn what we can learn from these radars.
Very cool. We've got a question here from our students in Ladue. Hi, go for it.
My question is, what is the process of recording data from a Doppler radar?
It starts with the radar. And this is going to be a pretty watered down version, but it starts with the radar dish like we just saw. It shoots the beam out, it sees the target, it was what we call it, and the target is also known, we call a hydrometer. That's a fancy word for rain or snow, or some sort of liquid that's up in the cloud. That beam radiates back energy, it absorbs energy from the radar and then re-radiates it out essentially reflects it back to the radar, and the radar this is all happening in the blink of an eye, by the way. The radar senses how much energy gets returned, and depending on how fast the return energy comes back, it can tell us the direction of movement that raindrop or snowflake is moving. It can tell us the size, based on the dual pol data. It can tell us the size of that raindrop or snowflake or hailstone. And then all that gets pumped into the computer. It does some fancy math. And the data is great, but it's only useful when we can see it on a nice computer screen with the colors. And so you have the processor that computes the radar data into the colors that we show you on the screen.
Great question. Thanks very much. And while we're on radar, I want to go to Carson Elementary School, New Jersey, because Darian has his definition of Doppler radar. We're going to hear Darian give that, and then we're going to look at some video to talk about that. So Darian, take it away for us.
The Doppler radar sends out a signal to a target. The signal bounces off a target, such as rain or snow, and sends it back to the radar. If the signal takes a long time to return, the storm is far away. If the signal takes a short time to return, the storm is nearby. The amount of signals returned indicates the size of the storm. The time difference between signals tells the meteorologist which direction the storm is.
No, it's a definition.
Well done, Darian. And that's an A. Oh, see? And the meteorologist is already giving you an A+, Darian. Make sure that your teacher can remember that information. That's about it, right?
That's it. He basically summed it up probably better even than I did on that. It got all the key points there. And it is without question for the life-threatening weather events, tornadoes, flash flooding, large hail, things that have very short lead times with the warnings, it is the most valuable piece of equipment that we have.
Well, that's a great transition to what we're going to talk about then on a bad weather day. The high impact day that we're going to focus on, April 22nd, 2011, Good Friday in St. Louis, was a day that became a very intense weather day. Now, before we begin to talk about it in depth, just talk a little bit about how far out do you know that such a day is coming?
We can have signs, big picture signs, a couple of days in advance. That the atmosphere may be setting up with the right ingredients. We look for instability in the atmosphere that's built up by heat and humidity, which would make the air very sticky and unstable. We look for signs in the atmosphere that the winds are going to line up. We look for wind shear in the atmosphere, and that's both in changing wind direction with height and wind speed. If the wind's increasing with height, and if it's changing directions with height, that can create a rolling motion in the atmosphere that later can get tilted when it runs into a thunderstorm. This horizontal roll that goes like this hits a thunderstorm, which is rising air, and it tilts it on its side like this, and that's where the tornado comes from. So we can see those big picture things developing several days in advance. The specifics we have to wait till the day of.
Okay, we mentioned thunderstorms. We want to go to some images, some animations of thunderstorms to talk about that, and then we're going to go to some more student questions. So here we have your towering cumulus stage.
First stage. This is where it all starts. Every thunderstorm starts at this point, and that's just like you'd see on any summer day in the Midwest or anywhere for that matter, where you have a lot of humidity and heat in the air. It's essentially like a hot air balloon. You get this bubble of air at the surface that, because it's a little warmer than the surrounding environment, it starts to rise. Those rising currents gradually cool as they go up through the atmosphere. That cooling creates condensation, and you get cloud development.
And so as it begins to develop, we go then to image 43, which is going to be, wow, now we're really blown up.
Yeah, this is a big storm. Now, this is your average everyday run-of-the-mill storm. This isn't one of the big supercells, which we'll talk about a little later. This is simply all that air that's been going up in those updrafts from the thermals. Gravity's still in effect here,
okay.
and air has weight. So at some point, gravity is going to say, you got to come back down here to Earth. So that air that goes all the way up starts to collapse down out of the storm. The updraft part of the storm is usually that dark cloud base where nothing's falling. It looks really ominous, but nothing's happening there. The part of the storm where all the wind and the rain typically is in the downdraft side, or the interface between the downdraft and the updraft. That's where the air collapses out. You get your strong winds, you get your very heavy rain, and also your hail.
And then eventually it just dissipates, as we see in the
Yes.
next image there. And
that's when gravity's finally taken over.
okay, we've got a variety of student questions that have been sent into us in advance about radar and about thunderstorms and storms. So I want to go up to Brady in Burt Edwards Technology School in British Columbia. Brady, what's your question about radar?
How does the radar make the pictures?
How does it get converted? How does the data get into those lovely images we see on screen?
To be honest, the technical side of that, I don't want to water it down too much. It's more of electro technology engineering type stuff. The computer, just like it creates a picture on your TV screen from a camera, the computer takes the intensity data that we get from the radar and then it turns it into colors. It's all mapped geographically using coordinates, and then it prints it out on the screen, just like your TV screen at home.
Right, and as we begin to look at this video, which just reminds people how radar works, the imagery, it's universal, like red is more intense, green is lighter rain, or is
mostly universal. Generally speaking, it goes from blue to green to yellow to red, with blue and green being your lighter rains, your yellows and reds being heavier, and then you graduate up to like a pink and white, and that's when it's like get out of town heavy.
Okay. You may or may not know the answer to the next question, but I was intrigued by it, so we're going to go to Carson Elementary School, New Jersey. Saul and Carlos, what is your question about radar?
What is the radius of the scan of the Doppler radar, and how fast does it go?
240 nautical miles in all directions from the radar. The one thing you have to remember with a radar beam is that actually the radar beam can go out forever, but its effective range is about 240 nautical miles. The radar beam, as it leaves the radar, immediately starts separating from the Earth. You have the curvature of the Earth. The beam shoots straight out. As the Earth pulls away, because it's round, the beam gets further and further and further off the ground, so that at a distance of about 80 miles from the radar, your radar beam's at about 10,000 feet or so. So you're well off the ground. At some point, generally about, depending on how big the clouds are, you're going to shoot over the top. But 240 is generally the useful range for big thunderstorms.
Very cool. And we had a question that came in via email from, again, Elizabeth Ann Seton School. When was radar invented? Is this
the first use of radar for non-weather purposes that I'm aware of was World War II, and it was misinterpreted during the invasion on Pearl Harbor. They thought it was a flock of, they either thought it was geese or they thought it was incoming friendly planes. It turned out to be the Japanese invasion.
Great questions. We want to go now to talk a little bit of questions that kids have about rain development and thunderstorms, which will lead into our understanding what happened actually on Good Friday. So we're going to go to Michael in Canton, Ohio, Arts Academy. Michael, what's your question?
How can you tell how long it will rain?
Well, sometimes it's as simple as looking at the size of the returns on the radar. If it's 50 miles across and it's moving at 25 miles an hour, it's going to take 2 hours to get through. That's an easy way of doing it in the short term. Looking at but sometimes rain develops over us, or there's nothing showing up. We still have to decide for tomorrow how long is it going to rain. Is it going to be all day rain or whatever? And so what we try and do is we look at the atmospheric charts, the weather charts, the synoptic charts, and say this is the size area, this is the general area that the rain should encompass. And then you look at that size and say, okay, it's moving at 30 miles an hour. Based on that and what we see the size should be, you kind of do a little bit of math and figure out that it should, the resident time, the amount of time it should be raining is 4 to 6 hours or something like that.
Cool. Good question. Thanks very much, Arts Academy. We're going to stay in Canton, Ohio for John's question about rain and temperature.
If the water is different temperatures, could it change the amount of water the cloud could hold?
Air temperature definitely changes the amount of water that the atmosphere can hold. And that's how we look at relative humidity. There's you have relative humidity and then you have absolute humidity. Absolute humidity is how much moisture is actually in the atmosphere right now.
Okay.
It's an absolute amount. Relative humidity is the percentage of moisture that's in the air compared to what it can actually hold. It's a lot like looking at a gas tank. A gas tank at 70 degrees for the atmosphere might be this big, and you have this much water. You take that much water down to 30 degrees, it's the same amount of water, but the tank is smaller. And because the tank is smaller, the percentage of the tank that's filled is actually higher. So you're looking at higher relative, same amount of water, but at cooler temperature, the relative humidity is going to be much higher.
Good. Thanks for all those great questions. We've got another question that I think is going to lead us into nicely what we're going to talk about with the development of really big thunderstorms. So I want to go to Strahan up in Bird Edwards again, British Columbia. Take it away, British Columbia.
If a cloud is held up by an updraft, would the cloud go up if the wind blew it into a stronger updraft, and would it go down if the wind blew it out of an updraft?
Just in terms of how updrafts and downdrafts work in cloud formations as they create, how do they work to create what we see as this big building storm?
Well, again, if you go back to the the slides that we showed of the towering cumulus clouds. Initially, it's all updraft, and that's the wind that's blowing. There's no downdraft, it's just all updraft. And it is literally, there's enough wind blowing up to hold all that moisture up in the cloud. The more moisture you start piling up further and further in the atmosphere, that's where gravity is going to take control. Now, what can happen in bigger thunderstorms with the right conditions, these supercell storms, which we'll talk about later, is with the wind shear tipping the cloud over a bit, you're actually able to throw more moisture up into the and more cloud up into the atmosphere and downstream, as opposed to collapsing down on itself. So it can prolong, changing winds with height can prolong the life cycle of the storm. I think that's maybe what he was asking.
Great question. A couple of terms we want you to understand as we begin to talk about then. And obviously here we're talking about building storms, and there's something called a supercell. So this is like really big time, oh my gosh.
This is a high impact weather day, right? Okay. Yeah. The original stuff we showed you were just your average ordinary thunderstorm development. It goes up, it goes down, rains out, and that's it. What we have here with a supercell is a situation where you have those changing wind directions with height. You have the wind going from southeast to at the surface down here where we are to southwest or westerly up at where the jets fly. So it kind of comes around in that direction. So you've already got the atmosphere twisting because of that. You also have speed shear, where that is the winds at the surface are weaker and they get stronger the higher up you go. So what you end up, instead of the straight up and down, where the storm goes up and then collapses down on itself, now you're getting that updraft tilted by the wind and twisted. So now as it all goes up, the whole storm starts to turn. And that's the beginning of the life cycle that could eventually spin up and tighten up into a tornado later on.
The next idea we want to make sure you understand is what's called a squall line, because that's going to be important as we go to some radar images as well. And a squall line is in essence the line of thunderstorms as they develop along?
This typically you'll see along a cold front. And typically what you're lacking here is that directional change in winds. You might have increasing winds with height, but you will not have the changing wind directions as you go higher. So instead of getting these individual rotating cells, you get this big wall, or line, if you will, of thunderstorms that we call a squall line. And these generally are marked on the leading edge by a low-hanging shelf cloud, and then a rapid temperature drop as that goes through, and then maybe 30, 40 minutes of heavy rain, lightning, and maybe some hail.
So there's some good basic information about thunderstorm development, squall lines and what they are, which are going to be really important to us as we think in terms of what actually happened on Good Friday a couple of years ago in St. Louis, where all of these things developed into a really blown up moment. I'm going to invite Chris to go over to that section of our studio where we're going to be able to utilize green screen. Thanks very much, Chris. And everybody, what we're going to have the chance to now do is actually see archived video of this day, where indeed these various parts of really intense thunder weather, storms and all sorts of good stuff came together on Good Friday. We knew there were going to be storms, and indeed storms were there. And the Doppler radar that we've been talking about before is what you're actually going to be able to start seeing now as we look at the Doppler radar from that moment in time. So Chris, I'm going to let you just take us through this moving Doppler stuff that we're looking at, incorporate some of these terminologies we've talked about, and then we'll look at those still images.
April 22nd, 2011 here in St. Louis was a high impact weather day. It was a day where we had all those ingredients for thunderstorms that we talked about. You had warm, very humid air. The air wanted to rise. It wanted to create these big towering thunderstorm clouds. But the difference that separated this day from an ordinary thunderstorm day were the other ingredients that I talked about for supercells. You had the wind changing with direction, the directional wind change from southeast to southwest to west as you went higher up in the atmosphere. And you also had that wind increasing with height. So the air in general was wanting to tumble in a horizontal tube like this. As these tubes of rolling air developed, they were in place as thunderstorms started to develop, those big, massive building clouds of air, updraft. That took that tube that was rotating like this and tilted it on its side like this. That's what creates the supercell thunderstorms. Now, supercell storms, when they develop, tend to be very discrete storms, very individual. You don't see this big line of red from northwest to southeast. St. Louis, by the way, is right here on your screen. You see these very independent looking cells, and as they develop out to the west, they start to get this characteristic hook on the southwest flank. That's the rotation of the whole storm coming together, and it's in that hook area as it starts out here. We're going to back this up. You can see it right here. That hook, as it wraps up and moves around St. Louis, coming across the radar site, hits the airport, the international airport here in St. Louis. That's the part of the storm that produced the tornado. And I believe we have some close-ups now. Awesome. All right, these are close-ups. Now we're looking at actually two different products. On this side of the radar, or this side of your screen, is the traditional radar. This just shows us how much of the stuff is out there, how heavy is it falling. And traditionally, again, greens and blues are light, yellows are moderate. You get into the reds and whites, that's heavy rain or hail. On this side of the screen, this is one of the cool things about Doppler radar, is it gives us the ability to look inside the rain, see what direction the winds are blowing. The radar site is this donut hole right here. Red colors are wind that's blowing away from the radar. Green colors indicate the wind's blowing towards the radar. And where they meet, that's an area where we have to watch for thunderstorms, and you can, or for tornadoes. And you can see in this area, you have departing air to the west, approaching air from the east, or from the east into the west. You can see it converging and starting to spin. That corresponds to this area, the developing hook or rotation starting to wrap around in this area. So that's the area we're watching for possible tornado develop. Next slide. We move you forward in time. You see how this is starting, this line really starts to zigzag on the winds. Wind blowing out, but starting to wrap around. Wind blowing in, starting to wrap around. This is the area right here where we're starting to really tighten up and intensify the circulation that eventually became the tornado. And really good look at it right here on the conventional imagery here, where this hook starts to wrap around. So you can really see kind of this fish hook developing, and that's where the tornado developed. I believe there's one more. Moving forward in time, you can see this is where the tornado actually starts to touch down. This is where you have it all coming together, all the right ingredients, all the right winds. Wind imagery here, strong winds blowing west and east, all wrapping around in close proximity. And the interesting thing is here, a lot of people think, they're looking at the radar and they say, shouldn't the tornado be up here with all this nasty color? Nasty color doesn't always mean that that's the worst part of the storm. Yes, it's raining heavily and there's probably some hail up here, but the most dangerous part of the storm in terms of tornado production is not up in here. You have to look down on the southwestern flank in the hook. This is where the possible tornado is going to develop, and in this case, this is where the first in a series of tornadoes that built up into the Good Friday tornado, a major destructive tornado in St. Louis, started to occur.
And the next slide we can bring up actually begins to show us what's referred to as the debris ball.
Yes, that's right. The debris ball is something you don't always see in a thunderstorm, and you certainly don't see it on a radar, but it's an indication of not just, as I said, the radar will see anything that it reflects off of. Most of the time it's hail and it's rainfall. But in this case, as we are getting right on top of the radar itself is just off camera, just right about in here. This area, because it's gotten so close, if you look very closely, you can see the wraparound right in here. That's not hail in the center. That's actually parts of people's homes and trees and debris being sucked up by the tornado. That's what's called the debris ball. You don't often see this unless the storm itself is very close to the radar, but we had a very good look at it right here. We are able to confirm a tornado on the ground because we could see the debris ball. Another look, this is an aviation radar out of the airport itself. It's a little different color scheme. There's the radar right here looking to the southeast through the storm, and we also see the debris ball right here. So on both of these radars, we have confirmation, even though we didn't have spotters seeing the tornado because they're in their basements, we have, in this case, a debris ball, a debris signature on the radar. So we had great confidence at this point there is a tornado doing damage in St. Louis.
Thanks very much, Chris. And you notice at the end of Chris's explanation there, he mentioned the idea of storm spotters. We're going to meet one in just a minute. But before we do that, you just did, in essence, a weather report right there. And Ethan's got a great question from Morales Elementary School in Pasadena, Texas, talking about how does you do what you do. So I'm going to go down to Ethan for your question.
Sir, do you have to memorize your actions and lines for the show?
Do I memorize my lines? You know what? There are some people who do try and memorize their lines, but when I do my shows, when I do my weather presentations, I know the story I want to tell with each slide. I don't just throw slides in or pictures in that don't have a meaning. Each one of them has to have a meaning, and I know what that is going in, so I know what I want to say about it. So that's part of the story, is to know what you want to say and have the supporting pictures, audio visuals to help you out. Obviously, you see behind me from this camera shot a big green wall behind me, all right? That map and those pictures that you saw, they were never here on this wall at all. I saw nothing on this wall, but we do a little process called chroma key where we send the picture that's being taken by this camera right here through the cables into the other room, goes through a computer. That computer rips out the color green, and says, all right, we got rid of this part of the picture. We have a big black hole. We want to put something in that hole. The computer slaps in, instead of this color green, it puts the map in. So that's what you see right here. Just what you see at home when you're watching your local weather person do the weather, your meteorologist. It's them in front of a weather map and not a green wall, but it's kind of smoke and mirrors in the TV business.
Thanks very much, Chris, and thanks very much, Ethan, for that question. We'll go to more spontaneous questions throughout the program. We've got some more email questions, too, that we'll be getting to. And don't forget, if we don't get to your email question during the program, don't worry about it. We'll be sending you email responses after the program, so don't forget to send them to us at live@hectv.org. Chris mentioned the idea of storm spotters, storm chasers, and we've got one with us today. George Weiss, come right on in here. Thanks so much for being with us today.
Thank you. Thank you for letting me be here.
So when we talk about weather, obviously, Chris is stuck in the weather studio, so to speak, and he's seeing all sorts of data, but he's seeing things that are coming from a computer, he's seeing certain things that are coming from the weather service, but he's not seeing pictures of the storm. You, George, are going to give him some ground level pictures of the storm. Talk about what it is a storm spotter chaser does.
Basically, a storm spotter, storm chaser. First, safety is first and foremost with what we do. I can't convey that enough. You need to be seeking shelter for the most part. With what I do is allow information to be passed through the National Weather Service with where we report to local weather stations such as KTVI here in St. Louis or in any of the other cities that are across the nation. But what's important in the field is getting the recognition that this is definitely a funnel. It's on the ground, it's defined, we can see the cloud formation, and we give that information to the authorities so that they can report it properly to keep you safe and keep everybody else safe.
As you talk about that, we've got some very intense and powerful video of is it a funnel or is it not. This is not from the Good Friday Tornado Day, but another day when you're out chasing storms. And George is driving across the Poplar Street Bridge, which is in St. Louis, crossing the Mississippi River. And we're going to see a tornado warning that's going on. You'll actually hear the sirens at some point in time. But this is what you're talking about. You're actually giving them the eye to the sky, so to speak, for us to learn. This is a wall cloud?
Yes, it is. And the warning had just gone out, so I had turned around. And you really don't want to be on a bridge in this scenario. So the first thing I'm really looking for is an exit. And you can kind of notice that I'm not traveling incredibly fast because I want to make sure that I'm safe and people around me are safe. My flashers are on. And then I'm getting all the information I can. In this particular shot, there's some obstructions behind, as you can see, the stadium. I can't really tell if this tornado is on the ground or if it's been confirmed yet, so that's why I'm approaching it. From what I understand later on, this actually ended up landing in Illinois and causing significant damage. So in terms of where you don't want to be, this is a perfect example.
It's a perfect example of that. I want to bring in Chris to add to this conversation. What makes a wall cloud a wall cloud?
It's an isolated lowering by definition. It's an isolated lowering from the base of the cloud. Now, there are different varieties of wall clouds. There's ones that's generally it's in the updraft part of the storm where the updraft is somewhat enhanced. It's the strongest lift going into the thunderstorm. But not all wall clouds rotate. If they're just sitting there, then you're not nearly as concerned about it as if it starts to spin. If it's just sitting there, you have more of an ordinary storm. And any storm can produce a wall cloud if it has a strong enough updraft. It's when it starts to rotate that your curiosity level and interest level really starts to peak, because that's when the storm has the elements around it to produce a tornado.
And that's what you're worrying about as you're out there.
Exactly. And also, we talk about rain wrap tornadoes and scenarios where, hey, it looks like it's not really that bad, but in fact, what's behind that rain curtain is something you don't want to be a part of. So,
well, we've just seen some video you shot through your windshield, so to speak, but let's go inside your car now to let the students see what exactly a storm chaser has with him. So we'll begin by going to image 36, and this is your setup.
Right. This is from 2009, but basically you can see my worn laptop, which is set up for streaming. It's been through quite a lot. It's battle worthy. We have a webcam, which is interactive with the laptop. We're set up to stream to an FTP site live, and then also there's a camera which you see mounted there, which is capturing images separate from the stream so that I can have them for the news agencies.
The next image we'll bring up, which will be 36, this is what you're seeing on the screen?
This is actually an application called Radar Scope. And Radar Scope is basically funneled information from the National Weather Service into an application for an iPhone or an iPad. And what you see with the yellow lines there are the counties that are outlined in a in a warning scenario, and then up in the, if you also notice at the bottom, that is the weather radar for St. Louis, KLSX, and that's just a base reflectivity thing there. And then, of course, in the upper right corner, you see the additional warnings for the area.
And as we look at this image, we'll bring that image back up for just a moment. Let's talk about warnings and that kind of thing, because, Chris, we've gotten some email questions about it. How do they designate how wide the warning area is going to be and those kinds of things?
They look at where they believe the highest threat is for the warned condition. In this case, you're looking at thunderstorm warnings. The box is yellow. If it was tornado warning, generally those are red.
Okay.
And what they do is they look at the zone where they think it's most likely to see severe weather conditions in the next 40 minutes or so. They also do include a fudge factor because they would much rather warn for a few more communities and have more people take shelter than leave a few out and have them get hit. So a lot of times warnings might be just a touch larger than the actual severe weather threat, just to make sure we get everybody covered.
Okay, the next image we're going to bring up, image 44, gives us an example of something that you actually see on your computer screen. And in this instance, what we're going to be looking at is from where tornadoes have actually landed.
Right. And this particular thing you're looking at here is from tornadovideos.net. Basically, there's something close to 3,000 different active storm chasers that are on the system. And that's my car right there with the little blue bar. And as you can see, the report for the tornado touchdown, because I confirmed that there was damage, is on the map. And then that information is then conveyed to the National Weather Service so they know actively what's happening. And again, that's on the right-hand side is just my live image. You can barely make out in the corner, but essentially that gives you an idea of what goes on for streamers that are out in the field like myself.
We had an email question that came in asking about your training. What is it that is...
Well, as far as training, I've gone to spotting school. I am a trained spotter. I have a spotter number, and the National Weather Service puts these on throughout the country, and I attended one of those classes and made sure that I understood what storms are all about, and was a certified spotter. So, and every year you go back and you renew your number and make sure you're in the system and all that, and we try to help out when and where we can.
And it's incredibly important. You know, we can look at all the great radar imagery and all the stuff the great tools we have in the office during a severe weather event, and we think we know what's going on. But until we get trained reports from our eyes forward, our eyes in the field, and even better, their video like this, we don't know 100% for sure. And I think our warnings and the ability to warn the public has increased dramatically with the use of this kind of technology because we have much more ground truth.
We've got a couple of images here, and I asked for this one specifically because from this picture, I don't know if that's going to be a tornado that's going to hit the ground or it's just a low-level cloud that's going down and that kind of thing. So from a spotter perspective, what am I looking at, George?
That's happening right there.
Okay.
And but again, there is obstruction here. And this was from St. Charles County.
Right.
I think this is from 2 years ago. I want to say that's right off of Jung Station Road, and that's near where the National Weather Service has one of their radars. And again, you know, you're not always going to see this. If people are out doing their business, you see people are just driving their cars and not even paying attention. But if your eyes are in the sky, you're going to see these things if you're savvy about the weather. So I take it seriously. I hope that everyone here takes it seriously, and I would hope they convey to their friends and family that it is important to be weather aware. So that's a great example of what you will see if you are paying attention.
So the two of them combine forces. And remember the video that we saw from the radar day. We've got Chris in the weather station, we've got George out and about, and we're going to see some images from that day now too, which will give you some video of what that looked like as they came through. But before we do that, I want to go to a question right here from LeDuc. Take it away, sir.
Hi, I wanted to know what the risk of being a storm chaser is.
Well, let's put it this way. I don't put myself in harm's way. I'm there to do a job, and that is to report the weather so that it can be conveyed to other people to stay safe. I'm not conveying that you put on a hockey helmet and wear hockey glasses to go out and cover storms. I don't do that type of coverage. What I do is responsible spotting and reporting. It's somewhat glamorized in other arenas, but what I do is just basic and simple. Just report what I see. If I see nothing, I see nothing. I have no report. But if it's out there, I'll definitely report it.
But it is not a zero hazard event. I mean, you saw with the first video he showed coming across the bridge, storms move erratically, and even people who are trained to know where they're going can find themselves limited by roads, and you end up steering yourself right into the track of the storm. So it is a high degree of there's a safety risk. There's no question about it.
Yeah.
And for us as meteorologists who are charged with the responsibility of warning the public, we greatly appreciate the risks that, not intentional, but are taken nonetheless, that is taken and undertaken by these folks to get that information back to us so that we can get more accurate warnings to you guys and the public.
Great question. Thanks very much. We're going to go to interactive questions in just a bit, but let's begin to now look at some examples of what these storms created. We saw the weather radar data, but we've got some video now from the area around St. Louis, outside west of St. Louis, called New Melle. And as we're going to learn in a little bit, this will be an EF1 tornado. But here's an example of actually a storm chaser, a storm spotter, doing the New Melle storm and seeing this tornado actually happening here. So this is from another storm chaser, one of your colleagues, Keith Weiss. But obviously, it's this kind of visual action that, Chris, makes a big difference to you. If you can see this in real time now, you know that New Melle is, I don't know, it's not more than 20 miles.
It's about 25 miles from the airport.
Okay, 25 miles from the airport. That's going to be important for us to remember as we talk about what happened on this Good Friday day. But this is beginning to happen now, and you notice that. Now, of course, we don't know. This ends up being what's called an EF1 tornado. EF being the enhanced Fujita scale that gives us tornado damage. You don't know what's going to be an EF1 tornado, though, at that moment in time. I mean, it could
We don't even know it's producing a tornado at this point because we have not received a report. This is the only known video of that entire tornado, of the tornado actually on the ground. We didn't get the video of in this case until after the fact, but this was the only visual confirmation we had of the tornado at the time it was happening.
So remember that image, because you guys may have questions now for storm chasers and storm spotters. And before we start to talk about damage from these storms and what is the Fujita scale, let's go to your questions. Let's go back up to Canada. Bert Edwards, a question from you?
Yes, we have one. Christian.
Did Doppler radar ever fail?
Does Doppler radar ever fail?
Absolutely. The radar doesn't see all the tornadoes, and that's the way it is. And the reason it doesn't see all the tornadoes is because, again, remember earlier we said distance makes a big difference, and the further away from the storm you are with the radar, the less detail you're going to have, and the further up in the storm you're shooting. Most of the tornadoes in the lower half of the storm. Once you get up over 10 or 15,000 feet, further distance from the radar, you're missing the key storm structure that would indicate to us if there is actually a tornado trying to develop. So the radar can miss tornadoes. It can miss small tornadoes if they're so small that they come and go before the radar can see them. And then, of course, they're susceptible to just like a computer.
Right.
In the case of the Good Friday tornado, there was real concern because that tornado passed very close to the radar site. Had we lost that radar site, we would have lost the ability to visually track that storm into the St. Louis area.
Good question.
In that particular storm, there was very few spotters, if any, available at that time.
Okay. So. Let's go to Canton, Ohio. A question from Arts Academy at Summit.
Where do the spotters go to wait to see if there's a storm?
Great.
Where do we go? Is it? Well, we try to be in a safe spot, and obviously when I was on that bridge, that was not necessarily a safe spot, but you always want to try to stay, in my best view is at least a mile or so away from storms. And that's hard to gauge because a lot of times they're unpredictable and they are somewhat erratic, but you definitely want to stay at least a mile or so back. And I think some people, they talk about position when a twister hits the ground and where do you want to be and all that. I don't want to be anywhere near it. So,
you would prefer to be as it's moving away from you.
That's exactly what you want to. Where you want.
So south and southwest of the storm is generally the safest area to be in position.
Exactly. Now this particular tornado, this was after the Joplin tornado. This was at a general store.
This is Sullivan, right?
This is outside Sullivan. So again, it's an image of, do I know that that's actually a tornado happening at that moment in time from this picture because of what I'm seeing?
Well, you can also tell it is rain wrapped, so it's difficult to see. I mean, you have obstruction because of the trees, but it is on the ground there.
So we've gotten some interactive questions. We're going to come back to our next two groups in just a bit, but we want to start talking about how you know the strength of the storm based on the damage you see. We mentioned the enhanced Fujita scale, and that is actually a storm with winds up to what if it's a 1?
If it's a 1, I think the winds are, on the spot on the exact number. It's like 70 to 90-ish for a 1.
And we're going to show you some examples of damage from that. So let's go to images 22, 23, and 24, which give you some damage from the New Mele tornado, and we can see what it is that happens when you look at something that's a number 1, almost number 2. So talk a little bit about this,
I should,
Chris.
for our Canadian viewers, it's miles per hour and not
That's
kilometers.
true, not kilometers per hour.
So
Thank you for that.
You all up there can do your math and figure out what the conversion is, because we unfortunately still use the miles per hour here. This is an high-end EF1 tornado. It's borderline 2. I would drive up to this, and my first thought might even be a low-end 2, looking at it, until I got into the storm damage itself to see what kind of integrity the structure had, what kind of parts of this building. It's hard to say, is this a garage that was, in fact, it kind of looks like that might have been the garage that was blown out.
And this one,
that's just a farm shed.
Lot less damage,
yeah,
obviously. So we're looking at something with not a great deal of damage on the EF1 scale, but obviously that's your barn, that's your house. It's obviously exceptionally important. But and this car here, this is an important image to kind of remember visually, guys, because this is a van that used to be sitting on the driveway there and has been pushed. You can see where the tire track marks are in the ground. EF1 tornado, and we ask you to remember that because in a little bit we're going to see what happens to a car in a tornado with a great higher intensity scale. So the ones that actually, in addition to this New Mele storm, we also had storms that crossed in what is called North County of St. Louis, very near the airport. And we actually have video footage from the security cameras at Lambert Airport, so you can see what it was like internally in the airport as the tornado was happening, and then we'll look at damage shots. Now, this is before tornado warning has been issued and people are standing in front of the big plate glass windows saying, wow, Dorothy, it looks like there's a lot of clouds and rain there. As you look at this, this is inside underground, first floor image. These are people in the lowest level of the parking garage attempting to enter into the airport. You're going to see the wind that's affecting them and what moves. And then the next section, it's security guards. You're going to see, again, we're inside the airport now, winds coming through. So at this point, the storm has definitely hit them. And when all of that is said and done, and we saw that that was over, what you end up with is what you're about to see now as you see what happened to those windows that we saw just a moment ago. The airport was closed for a couple of days as they repaired, and this is what we actually saw. So so you see kind of like being inside a big storm and then seeing what happened outside, and perhaps the aerial footage that we'll show you next gives you perhaps the most dramatic imagery of what happened that day on what is an enhanced Fujita 4 scale tornado. Chris, talk to this.
This is, and the difference between this 4 and the 5 that hit Joplin is enormous in that, we rate it simply by, if we see one area where there is EF4 damage, the tornado gets rated for the whole tornado as a 4. We rate it on its maximum damage. And in this area, we have classic 4 damage, especially up there at the top of the screen where that home is completely leveled. There's nothing left. That is classic 4 damage. A 5 would be, there's not even anything left except the concrete, the foundation. So that's the difference. In this case, we rate this as a 4. Fortunately, it weakened some before it got to the airport, or we would have had many, many fatalities at the airport. I'm certain of that. So this was truly a miracle that nobody was killed in that storm. The difference between that and Joplin was a 5, which is stronger. It's as big as they get, but it was also much wider. So whereas this was a very strong storm, it was very localized. Joplin took out a third of the city.
Almost a mile wide.
Yeah, right.
Joplin was almost a mile.
Well, let's do a bit of comparison. First, we've got an image we want to bring up. This is image 1, which gives you the before and after of that video area we just saw. So there is the neighborhood prior to the storm, and there is the neighborhood after the storm. So you can see the before and after in terms of what happened. Not even quite a month later, in Joplin, Missouri, they had an enhanced Fujita 5 scale, and as we begin to look at some images of that, you're going to see a different before and after. So look at this for a moment. This is Joplin, Missouri, the exact same block before and after the storm. So that driveway that you're seeing there between the garage and the house with the fence next door to it is where that man is standing in the bottom picture. All those homes have been taken away, the trees are gone, bark is stripped. Total annihilation and destruction, very dramatic, that before and after. The next image we bring up just gives you a closer view of that. And of course, the trees are not just being destroyed by the winds that are occurring as a result of the tornado. The trees are also being destroyed, Chris, by all the debris that's going around.
The debris is an underestimated damage component. People forget it's not the wind, it's what's being blown in the wind.
Yeah, the small pieces of metal, glass, sand, dirt. I mean, there were several fatalities based upon
people just
on
getting
debris
hit,
alone.
Right.
This image we wanted you to see to compare the cars. Remember that footage we saw of the van that had just been slid over before in the EF1? So here is EF5. That is the hospital in Joplin, which was pretty much destroyed by the tornado, significant concrete building. And then you can see what happened to the cars. And this is actually the helicopter, the hospital's helicopter, the level of destruction to that. So the difference you've got between an EF5 and just that van being pushed across on an EF1 level. Significant things to think about. And again, we don't know this for sure until we've already seen the damage.
Yeah, you know, we can look at it on the radar and we can see strong circulation, but there's no way, even to watch it on the ground, to know for sure that it's a 5 until after it's moved away. The thing is, the Joplin is a great example. It can go from a 0 to 5. In Joplin's case, it did it in a minute.
We've just got a couple minutes left, so I want to go to a couple more questions from students. So let me go back to New Jersey again. Carson Elementary, a question from you. Go for it.
Is being a storm chaser a full-time job?
No, it is not. I wish it was, but no, it's not. And what I do, as far as storm chasing is concerned, it is a volunteer part of what I do. I work as a news photographer, and I provide footage after the storms have happened to news agencies such as ABC, CBS, and the Associated Press. But I do my job as a spotter so that I can warn people that these things are going to happen. I mean, we don't want them to be the way they are when they turn off the way they do, but it's part of what the job is.
And let's go to Morales Elementary School, Pasadena, Texas. You guys get the final interactive question today. What is it?
Is it hard for you to determine the weather forecast? You have to know the present weather in order to determine the forecast?
It's challenging, and I take it very personally and seriously every day, even on a good weather day. It's challenging to read all the clues and get it right. We're not always going to be accurate 100% of the time. I think everybody understands that. We get that. But especially on high impact days, if I can give you at least an accurate representation of the potential impact, what could happen that day, and you're prepared, then I feel like I've done my job.
Well said. 90 seconds left in the program. You, young man, final question.
Hi. There are talks of more storms like Superstorm Sandy happening more frequently in the future. In your expert opinion, what is your take on that statement?
How much time? 30 seconds?
30 seconds for this, Chris.
I think as the atmosphere is going through a warming cycle, that heat energy will in some way, shape, or form be contributing to storm systems, maybe more storms. How intense and whether Sandy is a direct result of that, I don't think we have enough answers to that yet.
Any final words you'd like to give the kids?
You know, weather is fun to talk about. It's interesting. Fortunately, and for most of us, a day like today, it's an easygoing day. It's a non-impact day. But the problem is, when weather matters, it matters quickly, and you don't often have a chance to change your mindset. You need to be prepared for bad weather all the time.
Your 10 seconds, George?
And I think that mindset should be safety first, no matter what you're doing. If you're enthused about storms, think safety first, and make sure you stay aware of your surroundings.
Thank you very much for being with us, George.
Thank you.
Chris, thank you so much for being with us.
Absolutely.
Thank you, everybody here at Ladue Horton Watkins High School for allowing our program to be here today. To the great students' questions from Ladue, as well as our interactive groups. The program will be archived on the website in just about a week, so send your friends to hectv.org. Bye, everybody.